Okay, so last time we started talking about related rates. As one thing's changing, how is another changing? So we went over implicit differentiation, right? How am I supposed to take the derivative if I'm trying to take it with respect to time and that's not even in the equation? Well, we have to tack on a differential. How is radius changing with time? How is the height changing with time? That's what this dr dt and dh dt. Then we talked about, okay, well, what happens if something's being held constant? So if I'm not changing my radius, then literally the rate of change of the radius is 0. Like I don't need a dr dt if r is not changing. Okie doke. So I let you guys go like 7 minutes early last time because I wanted to go over this page in one swoop. So we'll see how far we get today. Yeah, okay. So here we go. Example 3. The base of a right triangle is increasing at a rate of 30 centimeters per second, while the height is decreasing at the rate of 2 centimeters per second. When the base is 4 and height is 3, find the rates of change of blah, blah, blah. Okay, so now it's our first real related rates problem. So we have a triangle. Let me draw the triangle out. Okay, one more time. So I'm going to draw the triangle. All right, so we have the base, we have the height. We know it's a right triangle, so I gotta put that 90-degree symbol there. And just for Pythagorean theorem's sake, we have side, and then the hypotenuse. I'm gonna just let the hypotenuse be C. Right, that's normally what when we use Pythagorean theorem, that's what we let the hypotenuse equal. Okay, so we have the height, we have the base, and we know the base is increasing at a rate of 3 meters. Okay. Increasing, height is decreasing. Okay, that's what I was looking for. So the height is decreasing. That means it's going down. So this length is shrinking, but the base is increasing. So it's getting bigger. So I'm trying to basically have a 2D image. And if you can imagine, this rectangle is getting wider and smaller. So like if it starts like this, the next shape would be something like this, and it gets shorter and shorter and wider and wider. So that's what's happening to our triangle. It's shrinking height, increasing width. Okay, that's why I drew the arrows that way. And we have at a specific time. So at a specific time, we want the rate of change. So it's kind of like we have, hold on. Okay, so I drew this. So this is showing a couple different areas. And you know what's really cool? Right now, actually for the last couple of years, Polaroids have started coming back into mainstream. I don't know, you guys see these Instagram people and they like have a Polaroid and then they take a picture of the Polaroid to put on Instagram. Why am I talking about this on math? Because a Polaroid, right, one of those little, it's just a little snapshot in time, a single instant, take a picture of your triangle, this is what it looks like. That's why I'm bringing up a little Polaroid, because that is the best way to describe this. So we're taking a little snapshot. When the base is 4 centimeters and when the height is 3, you're taking a picture at that single moment in time. That's what the height and the base are. We want to know what's the rate of change at that single time. So this is at your Polaroid instant. I don't know. Is this how you spell Polaroid? I don't remember. This is awkward. All right, your Polaroid instant. Because I showed you, this is literally 3 different pictures, 3 different Polaroids. I have when the triangle looks like this, when it looks like this, and when it looks like this. I showed you 3 different times. Okay, so I, of course, need space to actually do the mathy math, but I was visualizing, showing you what's happening with the triangle. Okay. So at our Polaroid instant, at the moment we want to know what's the rate of change, that's when the base is going to be 4 centimeters, and that's when height is 3 centimeters. Now, the height is not constant. It's not always going to be 3 centimeters, right? We just said height is decreasing, but at the instant when the height is 3 and the base is 4, what is the rate of change of? Then we go through the area, the length of the hypotenuse, the perimeter, the angle. Okay. Okay, so things we know. We said that the base is increasing at a rate of 3 centimeters per second. So the rate of change of the base. So we're saying, how fast is the base changing with respect to time? 3 centimeters per second. We also have the height rate of change. It's differential, right? The change in height over the change in time. That's all dH/dt means. It's how is height changing as time changes? Well, it's going down, decreasing at a rate of 2 centimeters per second. So this was context clues, right? You see 2 centimeters a second, you might miss the fact that it's negative because it's getting smaller. I think if I point out the tricks as we go through, hopefully you won't be tricked. That'd be great. Okay, so we have the rates of change, we have, the instance. All right, so now we're going to go back up to what we originally started with. Remember, we found, we took implicit differentiation. This is from example 1. We took implicit differentiation of different things, of circumference, of area, right here. Part B, we already did the work, right? We need to find the rate of change with respect to time. We already did it. We're going to do it again. All right, so we know area of a triangle is 1/2 base times height. And if I want to go through and find the derivative with respect to time, I'm being super extra, like writing everything out right now, just to show you step by step. So I want to know, how fast is the area changing with respect to time, right? What's the rate of change of the area? Am I increasing, 2 centimeters squared? Or like, how fast is my area growing? So we take the derivative with respect to time on both sides. All right. So on the left side, we have dA dt. And on the right side, we have to do product rule. All right, so I'm going to bring the 1/2 outside. I want to use like 50 billion colors, but like, okay, I'll do it this way. So B is my U, H is my V. So remember, product rule, we have U V prime plus V U prime. So this is going to be B times the derivative of H. Well, the derivative of H, right? The derivative is just 1, but then maybe H depends on time. So we'd have to multiply by dH dt plus V, which is H, right? I hate having like 5 different letters, but showing you U and H, right? Having that same product rule method, it helps. Okay, why is this popping? All right, times U prime. So the derivative of B is just 1. So technically it's 1 times dB dt, but I don't like writing times 1, right? It's a waste of time. So we say times however fast the base is changing times the rate of change of the base with respect to time. Okay, so I'm gonna just plug this in. So B times dH dt, right? You didn't need this over here. This was just throwing back, right? Product rule. Plus H times dB dt. Okay, so we have the equation. This tells us the rate of change of our area for any time, right? I could pick any snapshot, any Polaroid. Well, what about when base is 4 centimeters and height is 3? Okay, so we just plug in. So the rate of change of the area, that's dA dt. This is the rate of change of the area. So at our snapshot, at the snapshot, we have our base. Our base is 4, so I fill that in for B. Our change in height, dH dt, is -2, plus our height is 3, times dB dt. How fast is the base changing? 3. And then check that out. Ready? Just let's do the math. Do the math. 1/2 times, let's see, -8 plus 9 is 1. So the rate of change is 1/2. And we have our units. centimeters squared per second. I hate to use 50 billion highlighters, but you know. Let's see. So, right, DH plugged in here. We have DB, which we plugged in here. Do I have 4 colors? Maybe. B plugged in here, because this is at the snapshot in time. Because we don't know at this moment in time, this is the rate of change of the area. It's not going to be that way every single time, but at that single moment, when you took the Polaroid, looking at the triangle, when the triangle looks exactly like that, that will be the rate of change. Okay, so there's this part in black where it's like area, and then we take the derivative with respect to time, right? That's the way we started this lesson with way back in example 1. And that was so it became a little easier once we have a real problem and we have these rates of change and how the lengths, and we plug in. One thing to note is we do have an area per time. So the area are units squared over time. Right, and we saw centimeters per second, so that's how I know it's centimeters squared per second. And you should have the units. I'm gonna take a pause, see if you guys have questions. Yeah. So this is why I want to do the whole page together, because we're using the same triangle, the same rates of change, but the difference is between A and B, we're gonna have a different equation. Instead of having area of a triangle, we're gonna have length of hypotenuse. So we need to come up with an equation relating hypotenuse to the lengths of the sides. All right. I'm gonna scroll down maybe a little. Yeah. No, this is fine. Okay. I'm gonna redraw it. Okay. So notice I said snapshot in time. So at the moment we're interested in, draw this, and this is, okay, so of course I'm redrawing the general. You don't need to if you already have it drawn, but I'm just gonna show, okay, this is decreasing, base is increasing, we have a 90-degree, what do we say, 3 and 4, so let's see, height is 3, base is 4. This is what I did up above. And then this is my C, my hypotenuse. Now, the snapshot in time. At that instant, at the instant we're interested in, the height is 3, the base is 4, and we should figure out what's the hypotenuse. Maybe you recognize it's a Pythagorean triple. 3, 4, 5 pops up all the time. It's like, it feels like when math teachers or like books need to pick a Pythagorean triple, it's always 3, 4, 5. Sometimes 5, 12, 13, but most likely it's just a multiple of 3, 4, 5. Okay, so I call it snapshot in time because I don't want you to think the hypotenuse is always 5. Nope, only at that single instant you took a photo, that's when it is. I feel like I'm gonna cause people to stop using Instagram because I'm old and I'm just talking about it. All right, let's keep going. We need length of hypotenuse. So I need a way to relate hypotenuse to the two sides. Well, Pythagorean theorem. We know base squared plus height squared should equal hypotenuse squared. So once again, it's like, we're using the equation that's not new, right? You've learn this. We went over it in pre-calc. We used it in algebra 2 and geometry. You learned in algebra 1, right? This is your 5th math class where it pops up, which is why I didn't tell you, because by now you're like, oh, yeah, I know how to do this. Have a right triangle, blah, blah, blah. Okay. So here's the deal. We have an equation. Now we need to see how is it changing with respect to time. So let's go ahead and let's take the derivative with respect to time. Okay. Oops. Why do I do this? So I'm writing this step out. You don't have to, but I find it's useful. Okay. So all 3 of these things are changing, right? We said height is shrinking, base is increasing. Our hypotenuse is going to be changing as well because the 2 sides are. So we just need to go step by step, right? Term by term. So first, the derivative of b squared is going to be 2 times b. Because we treat it like a normal variable. You use the power rule, multiply and subtract 1 on the exponent, but we're not taking the derivative with respect to b, we're taking it with respect to time. So I have to tack on db dt. Okay. Next term. Well, the derivative of h squared is 2 times h, but then h probably depends on time, so we have to tack on, well, how is height changing with respect to time? So a dh dt. Maybe that's helpful. And lastly, you know what's coming up. The derivative of c squared is going to be 2 times c. And then we have to take into account how is our hypotenuse changing with respect to time. So because we're taking the derivative with respect to time, none of these variables is t. So we have to tack on, well, how is that variable changing with respect to the one we're taking the derivative with respect to? Wow, that's a lot of words. So one thing you note, we have a 2 blah plus 2 equals 2. We can go through, divide every single term by 2. It's just, you don't have to do it, but it makes it a little shorter. Okay. So b times db dt plus h times dh dt equals c times dc dt. Now this is very complicated. It is. Imagine a year ago, showed you this. You'd be like, what the heck? Imagine 2 weeks ago, I showed you this. What the heck? Right? So take a moment, tap yourself on your back, maybe like say it in your brain, like you got this, you work hard, you do good effort, right? Good self-talk. This looks complicated, but I know you guys got this, right? You have all of the tools you need, right? We know that, we know we know this is our base is 4. Our height is 3, and our C, our hypotenuse is 5 at the snapshot. So what we can do is just plug in. So I say at snapshot. Let's go ahead and plug in. So we know our base is 4, and our rate of change, dB dt. So we wrote that up in part A. That's going to be a positive 3, plus our height is 3, times dh dt. Well, we wrote that up above. That's negative 2. That's right? This whole page deals with the same triangle, which is why I want to do it in one swoop. C is 5 times dc dt. Okay. Ain't nothing, right? We just gotta get dc dt by itself. Find the rate of change of the length of the hypotenuse. So check it out, right? Not too bad. We have 12 plus negative 6. So this is going to be 6 equals 5 times dc dt. One step more. So let's say, okay, I'm going to write it this way. Yeah, I'll write it this way. dc dt, the rate of change of the hypotenuse with respect to time, is going to be 6/5 centimeters per second, because we need those units. 6 divided by 5. You could say 1.2, whatever. I mean, I prefer the fraction. So we had like all of this information. So for instance, these 3 things come from our snapshot. versus the others come from up above, the rates, because it's the height is changing at a constant rate. The width, the base is changing at a constant rate. So this rate of change of the hypotenuse is only true for this one moment in time. Okay, so part C is a little faster than part D is a little harder. So we need the perimeter of the triangle. This, I think this is pretty straightforward. You know how to find the perimeter. It's literally the fence, the length around the triangle. So the perimeter, okay, perimeter is just going to be height plus base plus hypotenuse. Those three lengths add together, that is the perimeter. So when we go through and we take the derivative with respect to time, oops, why do I keep doing that? So how fast is the perimeter changing with time? Well, that's going to be, and we take it term by term, the rate of change of our height plus the rate of change of our base. Wow, why did it erase that? Plus the rate of change of our hypotenuse. Because each of these terms, it's like, what's the derivative of h? 1 times how fast h is changing with respect to t. How is our height changing with respect to time? So secretly, there's a 1 times all of these in front, but like it just looks so much more messy. So we're using chain rule and doing implicit differentiation. Okay, ready for this? It's so short. So at the snapshot, I call it snapshot, at that single moment in time when the base is 4 and the height is 3, what is the rate of change of the perimeter? Well, you just plug in dh dt. How fast is the height changing? 3. Wait, is that right? No, nope, nope, nope. It's -2. Why did I switch them? -2. How fast is the base changing? 3. How fast is the hypotenuse changing? Check it. We just found it. Plug it in right there. 6/5. That's right. We already found at that moment in time. We know how fast the hypotenuse is changing. Just plug that in. So -2 plus 3 is 1 plus 6/5 is going to be 11/5. See, very short. The trick was, we found the rate of change of the hypotenuse already. We can find the perimeter. No biggie. All right, I'm gonna pause here, make sure we don't have questions before I go on to the next one. Water, give a little more time. Okay, so right now, you guys are doing hard stuff. All right, don't forget, it's a weird time, you're doing hard stuff, so don't get discouraged if this is confusing as heck. I'm not a motivational speaker, but I do want you to know that you're doing hard stuff, so don't get discouraged. All right, I don't want to give you a test until I know that like we're good. We're gonna have we have plenty of time. Let's make sure we understand things as we go. So if you're here right now, you can ask questions. If you watch the video, you can always email me a question or whatever, or ask in class next time. All right, this is the hardest one on the page. not necessarily because it's like actually hard, but it looks like it's difficult. And it's tricky, right? Because this is something we haven't done for 2.5 weeks called quotient rule. So same thing, I got this right triangle. Draw it out one more time. And right now we're looking for the rate of change of the angle. So what we're looking for is d theta dt. That's what we're looking for, the rate of change of the angle. Where the angle is where the base and the hypotenuse intersect. Okay, so this is the height, this is my base, this is my hypotenuse, and let's throw in right here, this is theta. This is the angle. It's between the base and the hypotenuse. Okay, so this is like the general, so maybe I should have been doing this the whole time. At snapshot, I call it snapshot. So at the snapshot, our base is 4, our height is 3, our hypotenuse is 5. All right, so we need some sort of relation. We need some sort of function that relates, an angle with some sides. We need something with an angle in it. So we could use sine, we could use cosine, we can use tangent, whatever. You have multiple options here, but you need a way to relate the angle with some of the sides. And personally, ready? If I use sine or cosine, I'm gonna have to deal with the hypotenuse, right? Sine and cosine have, okay, let me write that up. SOHCAHTOA, because I'm gonna justify why I'm gonna use tangent. So we're gonna have to take the derivative. And if I use sine or cosine, I'm gonna have to put a c because that's the hypotenuse. And we know the rate of change is 6/5. I don't like that. I mean, there's an easier way. If I use tangent, guess what? But the rate of change of the height, the rate of change of base, they're integer numbers, so it makes it a little easier for myself. That's why I'm going to use tangent. Because eventually, when I take the derivative with respect to time on both sides, the change in height, the change in base with respect to time is a nice number. Okay, so tangent of theta, tan is opposite over adjacent. It's going to be opposite height over adjacent base. And then when I run into dh dt and db dt, right, the rate of change of the height, the rate of change of the base, I'm gonna have like nicer numbers. That's why. You don't have to do tangent. You could do cosine, you could do sine. That would work as well. It doesn't matter. We're gonna get the same answer. I just, am avoiding dealing with fractions and doing exactly what I tell my students not to do. Avoiding fractions. All right, let's go ahead and let's take the derivative on both sides. So take the derivative, take the derivative. So the derivative of tangent is secant squared theta. And then, right, we took the derivative of tangent. And then we're like, ooh, we're not taking the derivative with respect to theta. It's with respect to time. So I'm sure theta, our angle, is changing with respect to time. And guess what? This is the magic bean. This is what we're looking for. All right, we're looking for this guy. All right, that's the left side. Woo, let's do the right side. So this is why I was like, oh, this one's a little like looks harder. We're gonna have to use quotient rule. It's been a hot minute since we used quotient rule. Remember that song I made you sing, or I like sang it to you? So it's low, D high, take high, D low, cross the line and square the low. Oops, why did I do that? Can't even read it. One more time. Low, D high, take high, D low, cross the line and square the low. That's quotient rule. So low, which is B, times the derivative of the high, derivative of the top is H. Okay, so the derivative of H is 1 times dH dt. Take high, okay, that's the one on top, which is H, times the derivative of the one on the bottom. Well, derivative of B is 1 times, how is B changing with time? So B d dt, cross the line and square the low. Okay. Perfect. So before I plug in numbers, I'm gonna get d theta dt by itself. I want the rate of change by itself. That way I can just plug, chug, and done. D theta dt is gonna be equal to b times dh dt minus h times db dt all over b squared times 1 over secant squared theta. You know, secretly, 1 over secant squared theta is the same thing as saying cosine squared theta. So if we can figure out what cosine is, we're ready to plug and chug. Because we know all the other things. So at the moment in time we're interested in, we know the base is 4. The change in height is, this is the one that's growing, so it's going to be 3. Nope, it's shrinking. Sorry, base is getting smaller, so it's -2 minus our height, which is 3, times the change in base, which is also 3, all over our base, which is 4 squared. And then I have to multiply by whatever cosine squared is. So I have this box here. I got to figure out what this is. Okay, so cosine of theta is adjacent over hypotenuse. Adjacent 4 over hypotenuse 5. So cosine squared is going to be, let's see, do I want to do this? Yeah, let's do that. So cosine squared is going to be 16 over 25. We're so close. We just got to simplify. -8 minus 9 over 16 times 16 over 25. Check it out. Let's cross out. We're left with -17/25. So let's write our answer nice. D theta dt is equal to -17/25 radians per second. Because we have a unit of angle over unit of time. Okay. This is why I let you guys out 7 minutes early last time, because I knew this page would take a while. We have done 4 different related rates problems. This is amazing. So the difference is, okay, now that we've done this, we have what, three pages of examples where it's like, I give you a word problem. You have to pull what's the important parts and right? This is like bare bones. So the strategy for solving related rate problem, understand the problem, right? This is why I said context matters. If it says decreases, you know that thing's going to be a negative. So identify the variable whose rate of change you seek and the variables whose rate of change you know. So this is why up here, I was like, hey, we're looking for d theta dt. Up here, I was like, check it out. These are the ones we know. We know the rate of change of the base and rate of change of the height. So most likely, the problem's not going to say dB dt is 3. It's going to be like the rate of change of height is 2 centimeters per second. You have to say, oh, okay, that's dH dt. You have to identify the variables. So identify the variable whose rate of change you seek and which ones you know. So understand what the heck is the problem? What is going on here? A big one is draw a picture. I I drew triangles. Oh my gosh. Well, it's not always going to be a triangle. Maybe it's going to be a cylinder. Maybe it's going to be something else, but draw a picture and label the parts that are important. Distinguish constant quantities from variables that change over time. This is why I keep saying like snapshot, right? I was like, nope, this thing is changing. I made it very clear that it's like, okay, at a single moment in time, those were the lengths, but not always, right? They were changing. Only constant quantities can be assigned numerical values at the start, right? We waited to plug in our values to we're like, okay, at the certain snapshot time. And here's the big one. You're going to have to come up with the equations. But it's like, it's not crazy, right? You're not coming up with a new law of motion for physics. It's things you know. Pythagorean theorem, perimeters, areas, volumes, surface areas, some trig, SOHCAHTOA. These are things you know. A lot of times geometric. Perimeter, Pythagorean theorem, right? Volumes, areas, surface areas. But it could be a scientific application. But a lot of it, you're going to know. You just got to think about, okay, what am I trying to find? Do I have an equation that has the thing I want and the thing I need? This is why we did tangent here. We have lengths of the triangle. We need to relate it to the angle. So that's why we use SOHCAHTOA. All right, differentiate both sides with respect to time. This is what we've been doing, right? We're pretty much pros at this by now. We've done 2 days of this. And then substitute values for any quantities that depend on time. So this step five are the lines that say snapshot. That's when I plugged in for everything. And I was like, okay, at the moment in time, at that instant, that's when I plug in for the constants, for the lengths, and the rate of change. And then interpret the solution, right? Literally have units. Does it make sense? If you find that your volume is 50 billion units squared, maybe that's off, right? A lot of these should be reasonable problems. Okay, I think we have, we have 10 minutes. That's enough to do this one example. And then, as I thought, it would take a third day. It's all good. Whew, all right. So this like method up above, like you can refer back to it. It's a step-by-step what to do. So a hot air balloon is rising straight up from a level field, is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation, the angle is pi over 4. The angle is increasing at a rate of 4.14 radians per minute. How fast is the balloon rising? Oh my gosh. Whew. Draw a picture. Draw a picture. Okay. So right here, here's my field. My hot air balloon is going up. So this right here is my balloon. Now the rangefinder is 500 feet from the liftoff point across the field. So right here is my rangefinder. And guess what? This, it's a constant. This is 500 feet away. The rangefinder, it doesn't say they're moving. They are 500 feet away from the liftoff point always. They are staying still and they're going to track the balloon rising. So it's lifting straight off. So we know this is a 90-degree angle. All right, balloon goes straight up. The rangefinder straight across 500 feet. It's helpful to label like, okay, the balloon is going up. So I'm going to say the height is going to be Y. I feel like once we draw the picture, it gets so much easier because then you can see what's going on. All right, and we said this rangefinder is tracking how fast the balloon is rising. So literally, this angle right here is finding how fast the balloon is rising. All right, so that's what we know. That's what we know from the picture. Let's label some things that it told us, right? It said that at the moment At the moment, the rangefinder's elevation angle is pi over 4. Okay, so this is like snapshot in time. So at the snapshot, theta is pi over 4. The angle is pi over 4. And it tells us the angle is increasing. Oops, why is it increasing at a rate of 0.14 radians per minute? Okay, so at that snapshot, at that moment, d theta dt, so the rate of change of our angle is 0.14, and it's positive because it's increasing. What are we looking for? How fast is the balloon rising? How fast are we rising? We're looking for the rate of change of our height, dy dt. That's what we're looking for. Okay, so let's think. Is there a way to relate what we know with what we want to know? Well, we need to relate angles and the sides. We don't know our hypotenuse. What we do know is the adjacent side, the opposite side. So I can is equal to y over x. And you know what? X is a constant. It is 500 feet. It's constant. The range guy, he's not moving. So tan of theta is just y over 500. X is not changing. The guy is not moving. He is staying put, finding how high the balloon goes. Okay, so let's go ahead and take the derivative with respect to time on both sides. So we have secant squared theta times d theta dt. And then if I have y over 500, that's literally 1/500th times y. So the derivative of 1/500 times y is 1/500th times how is y changing with respect to time? So dy dt. So we use the chain rule, right? At first it was, if I have 1/500 times x, the derivative is just 1/500th. But the issue is y is changing with respect to time, so we have to tack that on. Okay, to get dy dt by itself, you just multiply by 500 on both sides. Dy dt is equal to 500 times secant squared theta d theta dt. So I like writing dy dt, right? The differential left side equals blah, blah, blah. That's why I rearranged it a little bit. But now we can plug in. So at snapshot, we want to find at the snapshot, at that single moment in time, how fast is it rising? Well, 500 times secant squared of, well, at that moment, it's pi over 4 is our angle. And our rate of change is 0.14. So secant of pi over 4 is root 2. So if you square that, you just get 2. So 500 times 2 times 0.14. This is going to be 140. So dy dt is going to be 140 feet per minute. Those are the units. That was a little fast. Didn't need to do that. So we know secant of pi over 4 is root 2. So if I square both sides, it just turns into 2. That's why. And then 1,000 times 2, I'm sorry, 500 times 2 is 1,000. And if I take 1,000 times 0.14, move it over 1, 2, 3 times, so it's 140. That's how I did it. All right, this is a great place to stop. We went through 2 whole pages today. That's a lot of stuff, a lot of things to think about. Tomorrow, when we have class, we'll do a little review and then we'll go through. Rose, question?
For something like, I mean, I know it seems kind of simple, like the 500 times 2 times 0.14, and like I totally could do that by hand.
Oh, you could do it in your calculator. I don't care.
Yeah. Okay.
Yeah. Whatever. I just I don't know where the charger for my calculator is, so it's been dead for like 6 months. Yep. The one thing I do want to warn you about is right here, make sure calculator is in radian mode if you're gonna do that. Oh no, did I just freeze? Potentially. Well, good to know that. Well, my draw board froze. So yeah, just make sure that you, when you plug it in, your calculator is in radian mode if you put pi over 4. Screen sharing. Okay, cool. Well, my draw board just crashed. So I'll try to pull it up. Otherwise, we're that's it for today. And I'll see you guys tomorrow. If not,